Right? If you just do it, it'll turn out okay, even in our pandemic world. Hey everyone, I'm Today98, and welcome back to Talking Time with Caffeine, the only podcast where we drink caffeine and talk about whatever the hell we're talking about today. Today I have four guests. Two of them are brand new. Right from top to bottom, introduce yourselves, guests.
Hi, I'm Bent Hoven. You've seen me on Dapper Dino's channel on a show called Kent with Bent, and we love talking about Kent Hoven and why he's wrong. And I'm just here to enjoy a little more Kent and his take on evolution, which is quite wrong. Little spoiler. So
Hi, I'm Tony Reed. I have a channel called Tony Reed, and I host a show on there called How Creationism Taught Me Real Science, where I address creationist arguments from the beginning, from just not knowing anything and exploring exactly the science behind it. Almost uniformly, the creationist argument is completely wrong, but I don't market the channel to look that way. So if you end up watching 5 seconds of one of my episodes, I apologize if you ended up switching away. Anyway, I'll see you soon.
Hello, I'm Landon Kurt Knoll. A good morning, good afternoon, a good evening, depending on your time zone and latitude, from your friendly secular astronomer. I am an astronomer. My specialty is actually in planetary science, but in order to understand planets, you need to understand how solar systems form and evolve. In order to understand how solar systems evolve, you need to understand how galaxies evolve, and how galaxy clusters evolve, and then how the universe evolves. So you think of like planetary science as a culmination of stuff. What are the things the universe does reasonably well is make planets, and I get to study them. I get to study my favorite universe too, so yay.
Okay, so I am Eric Vierthaler. I go by Eric Vierthaler on I go by Eric Vierthaler 92 on YouTube. I've been on YouTube for over 10 years now. I started off as a movie channel, but I decided to branch off and do other things. I also do some debunking of young Earth creationism arguments. I do some debates with young Earth creationists. I also do a series on my channel called Things That Piss Me Off. It's a comedy series, where it's a version of me, where it's like an overly exaggerated version of myself getting mad at all like these simple, normal, everyday things in life. And so yeah, I'm going to be going to school for filmmaking and paleontology. And so, yeah, thank you all so much for having me here.
All right, so Eric and Tony, before we start, when you debated Ken about evolution or dinosaurs or whatever you debated him about, did he try to bring up these 6 things that are evolution, or I call Kent evolutions?
In my debate, no, because that was part of my opening argument. My opening argument was to quickly address that he's calling them definitions, and there's only one definition for evolution, which is change over time. Everything else is a context, and 2 of those just happen to be covered by a particular theory. But once I went through that, and I suggested that he should add one more definition, which is uniformitarianism, making it 7. He never addressed those definitions again for the rest of the debate.
But yeah, Kent never brought it up during my debate with him. Of course, he did still go through a script, but Kent Hovind has a lot of things under his script, like this 6 definitions of evolution. But yeah, I was just mostly surprised that he didn't bring up that behemoth as a dinosaur in my debate with him. But that is a completely different topic.
Well, as I say, I tend to focus on facts and observation, and my observation of Kent Hovind is that he's a man who's committed intellectual suicide. He has decided what truth is, and he will bend his perception of reality in order to make his truth work. You could argue why. Does it do it from a matter of faith? Is it a charlatan? You can decide. But but he's not interested in actually the facts. He's interested in pushing a narrative. Science is about questions. Religion and dogma give you the answer and say that's it, right? And if you don't do it, bad things will happen to you. Science is about questions, and it continues to question itself. And in fact, if you get a result, that just opens up more questions. That's the scientific process, right? And so his use on that slide I was seeing in front of me, he's using words in a pejorative sense for the purpose of his audience and for trying to justify his committing of intellectual suicide.
So now that we know that evolution isn't, that we know the Big Bang has nothing to do with animal biology, let's talk about what it really is.
Well,
so you want you have a screen share you want to share anything? You have a screen share or something? You just talk normally.
Let's talk normally. As I say, the time to have done that is we could do that at a later stage, like maybe a subsequent session. I can show you some things to discuss in terms of what we know about the Big Bang, the process before the Big Bang, the current universe. But let's talk about just in general what it is that has done. Cosmology has moved from a sort of a fairly imprecise science where measurements were very difficult and errors were large into a rather refined thing, largely due to the combination of observations, confirming models that turn hypotheses into theories. And again, from a theory standpoint, this is a common tactic that some people use. A theory is one of the is at the highest level of scientific validation. A theory is a statement which is falsifiable, that has passed many rigorous tests, right? It takes a long time for something to elevate to a theory. So when someone says it's just a theory, it's like saying it's just truth. It is just perfect, right? Its theory is as high as you can get, and so the Big Bang theory. If you want to use colloquial terms, I don't like to use it, but you say the colloquial terms is established scientific fact. I don't like to use that term because again, I think theory is a better thing, because also theories can be refined and deeper understanding can evolve because you continue to ask questions. You don't commit intellectual suicide like Cy and Ken and Kent have done. You let the data drive what happens. You let the data falsify, discard models, and
you can admit when your data proves that you're wrong.
Absolutely. Scientists get really excited when they realize that they don't understand something. That's the most exciting thing, is when you realize you don't understand, because to know you don't understand is a very powerful thing, because it allows you to begin to learn. If you are given a book written by ignorant savages saying this is truth, take it or leave it, or go to hell, then you don't have any learning, right? But science is about, scientists really get excited. So when we discovered, for example, the amazing situation that the universe was accelerating in its expansion, that was a really exciting time, because now we don't know a bunch of stuff, and there's the questions. The questions drive science. It's all about questions. Dogma and religion say, no questions. And in fact, religion has had a habit of putting people in jail for asking the wrong questions.
So
science gives them awards.
So if I want to chime in on just the theory thing, by that same logic, I guess that atomic bombs do not work with atomic theory, and neither does gravity work, because that's a theory too. And so we all have heard creationists say, oh, well, evolution is just a theory and Big Bang's just a theory. Well, to my surprise, there even was one time when I have even heard like a non-creationist say that the Big Bang is just a theory.
Yeah.
And that shocked me.
But it's part of the thing. It's part of the problem of I guess of education.
Yes.
We torture kids too much in memorizing addition tables and not enough about actual asking questions and exploring. That's a and you might argue that things like flat Earth stuff and religious stuff is a sign of a failed education system.
Yeah, which I definitely do agree that our educational systems have failed us, which is more than likely why that we have seen a revival in the movement of the flat Earth.
Yeah, I think of all the things of topics of things of flat Earth creationism and stuff. I think the most dangerous of all is the anti-vaxxers movement.
Oh yeah, big time. Yeah.
Big time. So I tend to not debate facts. I mean, debating facts is kind of a silly thing to do. It's a waste of time. And so I like to look at, I like to study, I like to ask questions, and I like to explore, which is why, I'm a scientist. I get to explore my favorite universe and amazing things that are in there. And when you begin to explore some of these mysteries that look there, you ask questions and you see some of the results, your wonder increases as your knowledge increases. It isn't as if you explain it and everything's then all done. And in fact, your wonder increases, and the more questions, right? The more you know, the more questions you have. The more you know, you don't know, and that's like the wonder of science. And so Big Bang and cosmology has a number of areas we're working on, a number of areas where there's new questions, because again, science is about questions. We have a number of answers that have gone and confirmed to extraordinary degrees of stuff, but Big Bang cosmology is extraordinarily successful in its prediction and observations confirming it.
So Kent mentioned it in one of his, I think probably Dapper and Bit probably talked about it in their Kent with Bit series. Well, how I remember one of them where he says the universe apparently was shrinking. He was making fun of how it was shrinking to from this big to this small when it was beginning.
I mean, there's been various models, and some had oscillating, things. But back when I went, when I was in college, the debate was whether the universe was open or closed. Right? It would be open and expand and go forever, or halt and come back and forth and oscillate. And it turned out that we were asking the wrong question. In fact, the universe appears to be accelerating. And in fact, if you say, what's the Big Bang? Well, first of all, you understand the Big Bang was a name coined by Hoyle, who preferred the steady state theory and who sort of dogmatically held on to it and used it in a BBC radio series as a way of derisive stuff. But the name kind of stuck because it sounded kind of cool.
Yeah, and that's the thing about scientific names. Once they're there. Like dinosaurs, they're terrible lizards, but not really lizards at all. But now people are like, oh, they're lizards, but no, they're not.
Yeah. So in that sense, the Big Bang didn't go bang, right? And when it started, the visible universe wasn't big, right? That's kind of it was used in a pejorative sense. So in some ways, it really is more a matter of talking about an event in what we call in the inflaton field that caused the universe to rapidly expand over a very short period of time, and then slow down, and then begin to cool and go through various phase transitions to see the universe today. And it made a number of predictions. The Big Bang hypothesis made a number of predictions that were confirmed by that. And you can see the Nobel Prizes that came from confirmation stuff, such as a prediction of the cosmic background radiation. The sea of microwaves, which is a result of a thing that happened 378,000 years after the Big Bang. But you talk about small, right? The Big Bang theory says that our visible universe, the stuff we can see, was once very, very small and compact, compacted into a super dense state, much, much smaller than the size of an atom today. And that there was a period of what we call inflation, where for the first 10 to the minus 30 seconds. That's a 0, 0 point, and you have 29 zeros in a 1 second. The universe expanded by a size of about 10 to the 25th. That's 1 with 25 zeros on it. It rapidly expanded. The expansion halted, and in fact, then the universe went through various phase transitions. We know fairly well what the universe looks like today. I mean, we can observe it, right? And we have a pretty good idea about what it is. We have actually a pretty good, pretty solid explanation of how matter and space works back to about the first trillionth of a second after the Big Bang. Why? Because we can actually recreate those conditions in our particle accelerators, like at CERN. We have it's a little bit fuzzier around 10 to the minus 30th of a second. And it's this book where we're peeling back the pages, looking back forward, and we actually have some pretty good explanation as to what happened before the Big Bang. So, that's sort of the state of the world. But I can answer questions about stuff.
From what I heard, I'm not sure not, but from what I heard some people say that at first it was no matter, just energy.
Well, by matter, you're talking about baryons, like the atoms are full of protons and neutrons
like
and electrons,
and
right?
Stuff.
The state of the baryons actually didn't form until a few minutes after the Big Bang, because the universe had to expand and cool to the state where the energy fluctuation allowed for particles to form. And that's so there was an era, that early era, there was just a sea of radiation, and pre-inflation, the universe was relatively uniform. That is I saw the visible universe was our visible universe was small enough that particles could travel back and forth. One side, if it got a little bit hotter, could transfer its heat to the other side. That it was small and compact enough that could happen. And when inflation occurred, and that's, you see this inflationary period here, and this is a model that says minus 10 to the 23rd or minus 20. I mean, that inflationary period that occurred, and we're narrowing down the time of inflation. I mean, the best I said right now is that in about that 10 to the minus 30th, first 30th second, a very, very small amount of time after the Big Bang, the universe expanded to the point where it was where now things were too far apart for one part to affect the other. You can get quantum fluctuations. Quantum mechanics says that you don't get a perfect level. You can get oscillations, and because things were far enough apart, those oscillations began to not uniform, not equalize. Right, you get hot spots and cold spots, and that is what you see moved on there. So as you see the temperature, and this particular article talks about the fact that these particles, in terms of seconds, right? It's saying about the first 10 billionth of a second is when the particles started forming. When quarks and stuff could form the very first nucleons, the baryons, and as the universe expanded and cooled, those particles formed plasma, and then the big thing that happened is at around 380,000 years, when the universe dropped about 3,000 degrees Kelvin, we went from a plasma gas to a transparent gas. That transparent gas let the photons that were all bound up escape, and that microwave background was one of the amazing predictions that the Big Bang Theory predicted that was confirmed.
Is that the thing they found in that satellite dish? They were trying to.
Yes, and Wilson, Vincent Wilson, using a what was then sophisticated microwave telescope, found this sea of radiation. Now, if you have an old analog TV set and you tune the TV set to a channel that's not broadcasting or between channels, you see that static fuzz, right? I'm not talking about digital TV. I'm talking about the analog TV, the old aerials. You see that snowy fuzz on there. About 1% of that fuzz are these microwave photons striking the antenna and inducing a charge in your TV set. So we can still hear that hiss today. The telephone company was trying to look at doing microwave transmissions and was noticing this noise, this constant noise, this static, right? They were thinking they could do these telephone links across large distances without having to drag copper wires. And they kept hearing all this hiss and noise and what's the source of this noise? Why is there all this hiss, this static, annoying static? And it turned out it turned out it was actually coming from the sky, and it was actually something that the Big Bang predicted that we actually discovered. But there's more than just this noise. It went and talked about hot and cold spots, and these spots had to do with something called baryonic acoustic oscillations. In this early plasma state, the electrons were too energetic to bound into nucleons. We just had a bunch of nuclei, a bunch of electrons, and a bunch of photons. Right? We're talking about the normal baryonic matter, and these photons couldn't get anywhere far because charge, this charged soup of electrons would absorb and reflect the photon. So the photon couldn't actually go very far before it was being deflected and bounced around. You couldn't see straight. Everything was just a giant fog. And when the universe cooled to the point where a proton, nuclear hydrogen atom, could grab a whole electron and form a hydrogen atom, it became neutral and the photons went free. And the universe that visible universe has expanded by a factor of 1100 since the time of that event. That's at 370,000 years after the Big Bang. It's expanded. And that we know when we take hydrogen, you can take hydrogen in a gas and you can heat it up to the point where the electrons boil off and you get that nice glowing arc. It looks like a neon sign, but it's a hydrogen sign. Hydrogen too, it'll glow. We know what energy it takes to kick off the electron. Well, you take the temperature today of the universe, 2.7 degrees Kelvin, and you run it backwards. And this was something that was actually first extrapolated by actually it was interesting was a physicist who was a Belgian priest, and you run it backwards, you run the universe backwards, and you find the universe gets hotter and hotter and hotter. At 370,000 years, the universe is at that temperature where hydrogen turns into plasma, right? You no longer have just this nice neutral gas. And we see the result of the photons scattering off of that as this microwave background. So one of the things in particular, we talk about, this how do you know this Big Bang stuff? How do you know they weren't there? We can see it. When we look back in the universe, when we look out in the universe, we're seeing back in time. And we can measure that thing. We can actually, and the theory makes prediction about oscillations and that stuff. And that's another very important point that will tell us a lot about the early Big Bang, and we can accelerate it, go even back to the point of a trillionth of a second.
So how do we know? How do we know how long ago the Big Bang was? That was like 13? Was it now 13 billion years ago or something?
Well, the current thing is about 13.78 billion years plus or minus 130 million years. It's kind of that's a margin of error that we have on the measurements. And it started with people like Hubble, Hubble and Lemaitre were talking about possible universe expansion, and Hubble actually measured that the universe is expanding, and Lemaitre was a physicist that said, well, if the universe is expanding, let's say it's from now it's going on there, well, what happened before? Well, if it's expanding, it means it was smaller and smaller and smaller. You just run the clock backwards and see when, and if you do that, your visible universe gets smaller and smaller and smaller and smaller and smaller, right? And he said, well, that would imply to go back to a point. Now, general relativity was happy to say, okay, it goes back to a singularity. But quantum mechanics says, no. You don't. There's other things that stop you from just crushing back to an infinite point. And so therefore this is sort of the process of saying, well, the universe must have started from a very small, the visible universe must have started from a very small, compact, high temperature and went through phase transitions. And so if you look at its temperature and you run it back to the point where you would see the microwave, you'll go back from 2.7 Kelvin down to 3,000, up to 3,000 Kelvin. And you look at how the universe is expanding, and you just run it backwards. It gets smaller and smaller and smaller. You just run the thing backwards down to the origin, and it'll tell you what it is. Now, it turns out it's not quite that simple, because there's a thing called inflation, which causes it to curve a bit. But we can measure those curves. We've measured the dark energy and what it's done to it. And so we just basically take the current state of the universe that we can observe, run it backwards, and you end up with this 13.78 billion years. Now, there's other methods you can also derive that, but that was one of the first predictions, was that the universe would be about that thing. And as we got better measurements, we're reading more and more precise on that thing. As we understand the physics more, and we use things like particle accelerators to create, bits of space that are like trillions of degrees Kelvin, and observe what it does, we can now tell what happened a trillionth of a second after the Big Bang.
And going back to that whole argument about were you there? So even when I was a young Earth creationist, I never used that argument. It was because even when I was a young Earth creationist, I knew how bad of an argument that was. It's because, say if you found footprints in the snow, even though you weren't there, obviously you know that there was somebody there, to make those footprints. So yeah.
And now the Big Bang theory talks about what happens after the Big Bang. In order to happen what before the Big Bang, you need to go to inflaton theory and inflation theory. And inflation theory predicts that there has been multiple Big Bangs, and one of the interesting about inflation theory is that our universe is one of many. Our universe is one of these inflation bubbles, mini inflation bubbles, and that we are in essentially an eternally inflating greater universe. Our visible universe is part of a larger universe that's not visible, because there hasn't been enough time for the photons to reach us yet. But our universe is part of a larger, greater, internally inflating universe. It's kind of this model, and so the inflation field has made some predictions. Lindsay Elbrick and Steinhardt in 1982 has proposed a thing called slow roll inflation, and there are current experiments going on at the South Pole called BICEP that is going to measure one of the predictions that slow roll inflation model suggests. Right, the slow inflation model can, if the measurement doesn't work out, the slow roll inflation model is thrown out. But if it survives this stringent test, it'll be remarkable. And in fact, the slow roll inflation model has predicted that we're going to measure certain things in the early universe from the microwaves, and we're going to see if that's actually true. And so it asks questions, and we're going to verify we'll look at the data to see if it fits in that thing. And if it does, that'll really advance forward slow roll inflation. But that's, again, one of the exciting things that'll happen probably in the next year or two. I know when I was there last in 2018, the people that were running on BICEP 3 were that's a telescope, were very pleased with the performance of the instrument, and they're gathering lots of data. And BICEP 2 came up with some interesting things that was in line with this model of inflation, but there are other things that could explain it. So they said, okay, we're not going to announce success yet. We're going to do this other measurements. We're going to rule out something called dust, which is causing complications. And they have a way of ruling out that dust. And if it turns out it survives this very strong stringent test, then it'll be very good for slow roll inflation, which will explain stuff. But understand, we still don't. There's a lot of stuff we still don't know. And that's okay, right? That's science. We don't know whether the universe is infinite or not. We don't know about a great deal about what happens before the Big Bang, but we have models that are making predictions, and we're trying to test those models to see what survives and what doesn't. But that's science.
So was the quarks the first matter that was ever made?
I mean, when you bring the universe back to very, very high temperatures, you find that this thing called a strong force, the weak force, and electromagnetic force become sort of unified. And at that stage, the somewhere there out of that soup, of the energy soup, quarks form. But again, we're talking about things that are probably somewhere on the order of around 10 to the minus 35th of a second after the Big Bang. Very, very short. Again, we can go back to about a trillionth of a second after the Big Bang with major certainty. The other stuff has to be sort of inferred, and we're working on it. Again, that's part of acceleration and part of physics. But right now, today, the situation is such that we don't have free quarks. But we think you had sort of this quark gluon glue, this sort of quark gluon plasma, probably very early on in the universe, and we're doing experiments at places like CERN to try to see if we can confirm those models.
Say CERN.
CERN, the particle accelerator at
Oh yeah,
CERN.
it's funny because off topic real fast. Fiction. I'm playing a video game on PS4 where CERN is a bad guy.
So as I say, in many ways, if you think about the Big Bang as his book, we have a very good idea about most of the chapters, and down to the first page, we have a pretty good idea about that story. But we're working our way back through the sort of the last page, the last trillionth of a second is where the current research is going. We have a pretty good idea. We can recreate that and we can test that, and those models have survived. There's some new stuff that's going to push us back to even further. And but again, that's in terms of what happened in the Big Bang process. Prior to the Big Bang, the most likely thing is you had an inflation field, and you had this oscillating inflation field, and likely you had multiple Big Bangs going off at various different times. Slow roll inflation allows those Big Bangs to occur far enough apart that they actually don't run into each other, right? Because one of the things that originally they said, well, hey, we just have the inflation model. You had these things popping in, these rapid expansion of space, but they should have then ran into each other. We should see in the sky these inflation bubbles smashing into each other and creating all kinds of interesting patterns. We don't see that. Slow roll inflation means that these inflation bubbles, like our visible universe, were done far enough apart they don't run into each other. And they also make some other predictions, which we're testing, right? Again, this is again how these sort of processes work. There's a prediction about how the photons scattered, the last bounce of how they, before the plasma went transparent, what happened to those photons. And there's a very specific prediction that if it's shown to a high degree of certainty, will lead credence to the slow roll inflation. And so it's from an Einsteinian point of view, the pure relativity, the Big Bang started time, and all the world lines go back to an infinite point. But we know that that relativity has limitations. As great as a theory it has limitations in terms of conditions. Just like Newtonian mechanics is not wrong, it's just not useful when you get to very high energies and very high velocities and very high temperatures. Same thing with relativity. When you get to extreme stuff near the edge of a black hole, when you get near the Big Bang in time, it begins to break down in those extreme conditions. And so people are working on that to try to solve that. But again, what in a nutshell, what was the Big Bang? The Big Bang was an event out of the inflaton field where a particular space rapidly expanded. And the best model is expanded into what? It's not that it expanded into anything, that you had this larger, perhaps higher dimensional space where inflation started. The inflaton field fell down, right? It was at a higher level, and it dropped. And as it dropped, it particles, the virtual particles became real particles, and it caused the universe. That process had a rapid expansion that then slowed down and stopped, or slowed down. The inflation process slowed down. Now we have this inflation field is called a scalar. Fancy word for you can assign a value to every point in space, right? Just like a scalar field of temperature, you can measure the temperature at spots and assign numbers. The Higgs field is a scalar field that is responsible for giving particles that travel less than c, the speed of causality, or the speed of light in a vacuum. That's a field that gives those particles mass. But there's another field, which is called the scalar, the inflation field, that is responsible for the inflation process, right? So what happened before the Big Bang? Well, there is this eternally inflating universe that had fluctuations where you had things at a false or at a high level, and those began to drop and result in when they dropped, the virtual particle became real, and out of that you have your observable universe. It makes a number of predictions we can verify. We can see scales on the large scales of these rings of galaxies, or the spherical shells of galaxies that map to the baryonic the oscillations inside that early universe. I mean, prior to in the early phase, prior to 370,000 years, when you had this giant plasma, right? The first 370,000 years, you had a giant plasma. You had sound waves moving through the universe at about half the speed of light, and those sound waves created bubbles, right? Oscillations, and when those bubbles cause sound waves, when stuff squeezes together, it gets a little hotter, and when it pulls apart, it gets a little bit colder. When we look at the microwave background, we can see these very subtle cold and hot spots. And in fact, we can see the angle that those things make. They're around about 1 degree in the sky. They correspond to about 500,000 light years. Expand the universe back another 1,100 fold. Why? Because we know how big it is. We know how fast it's going. We just run it backwards. You just run it backwards down to the point that collapses it by a factor of 1,100, and you get the smallest thing. So when you see these 550 million light year shells of galaxies, and you run it backwards 1,100 fold, you get these 500,000 light year bubbles that we can see in the microwave background. We can see the oscillations occurring because we can see these fluctuations in the microwave background. It's very subtle temperature changes, but they're necessarily there. And so we see today the large 550 million light year size halos of galaxies that came from the early bubbles that at 378,000 years were only 500,000 years across. And furthermore, there's many predictions that this model makes that we can then verify in we're not just making this up. I mean, that in order to make these claims, you have to have extraordinary evidence. And the models that fail, that run contrary to observation, get tossed out. But the ones that stand the test of time over and over again, like the Big Bang Theory, get elevated to the status of theory. And again, marvelous confirmations of that stuff. Do we know all the details? No, because when you learn something, you then ask more questions. But that's science.
So when exactly did it become a theory, officially a theory?
Hey guys, sorry to barge in, but But I have to head out now. So thank you all.
All right. Thank
See you later, Eric.
I mean,
All right, bye.
Good seeing you.
Yeah. I think that's that's probably the early. I mean, the early. You can talk about this. We can talk this at another time in terms of how that thing was modeled. But in the 1920s, there was a physicist that took Einstein's general theory of relativity equations, the state, basically the equations of the universe, and looked at the implications and came up with early hypotheses about inflation. There was a thing called cosmological constant that Einstein had to put in his equation to get them to balance out, which he thought was not needed when they found the universe was expanding. The problem is it is needed because the universe is expanding faster. There's this repulsive force that was surprisingly discovered there. But the early parts of the Big Bang probably go back to the 1920s. It was started from general relativity, which had its roots in special relativity, has its roots in places like Maxwell's equations and further back in time. But again, it's all built on top of each other. But I think the first roots of it came in, and then of course the Hubbles had the first notion that it was the universe expanding, that these nebulae, these glowing sea of stuff, were not just gas clouds, but actually other galaxies, right? Because prior to Hubble's discovering that these little whirlpool things were actually other galaxies, we thought the universe was our galaxy, right? We thought that was it. And now we realize these other things are actually our galaxy. And how did it do that? Because telescopes got good enough, we could see individual stars in those other galaxies, right?
So this would not be possible in a geocentral universe, then would it?
No. I mean, again, that's another fact you just it's not worth arguing over. And you can, it's a fact that the Earth goes around the sun. Actually, sun and the Earth go around a common point that's inside the sun, but for all practical purposes, the sun moves a tiny bit and we move a lot in 1 year. Right? They do this dance. Now, I mean, a better example of that is the dwarf planet Pluto and its moon Charon. They kind of go around each other like that, and so we call them a double dwarf planet because the point that they go around is kind of in between. And again, the motions of stuff can be exquisitely measured. And we can see the effective motions of the Earth relative to the Sun, and so it's a scientific fact. We've gotten over that several centuries ago. But still, I want to emphasize saying that this Big Bang theory has stood many tests, right? That's why it's elevated to a theory.
Yeah, you mentioned that scientific theories or scientific findings and theories are built upon each other. Yes,
I mean, again, the things that happened, for the relativity, part of the seeds of relativity came from Maxwell's equations when we were studying electricity and magnetism. In fact, the speed of light can be derived from Maxwell's equations and major properties. And that's the odd thing was that Galileo had a principle, a relative principle that said that physical processes go on regardless of their motion. Right? If you have some chemical reaction in a beaker, it's the same whether the beaker is moving or still relative to you. Right? It was this equivalence principle, is what he called it. And it turned out that was actually not complete. There were things that didn't do it. And in particular, Einstein, looking at Maxwell's equations and looking at things like the Michelson-Morley experiment, said that it appears that the speed of causality, which happens with the electromagnetic radiation light happens to go at in a vacuum, that's the sort of fastest you can do, that speed is is a universal speed that's independent of how fast you're moving. So if you have a car or a spacecraft that's coming at you at, let's say, half the speed of light for some reason, or you got some super duper fast thing, and it shines a beam of light at you, that beam of light doesn't hit you at 1.5 times the speed of light. It hits you always at the speed of light. The light always goes the speed of light in a vacuum. So more like, think about causality. Causality, stuff in this region of space that causes the next region of space to change. That propagation of causality happens at a maximum rate. That's what C is. And electromagnetic radiation in a vacuum is moving electromagnetic waves. That causality is happening at the maximum speed. And it turned out from Maxwell's equations, the speed of light is constant no matter whether the thing is moving relative to you or the same. You always see light, whether if it's receding. Now, it may be stretched out, maybe a Doppler shift, but the speed that the photons run at you is always C, no matter how fast you're moving relative to it. And that causes you to have to abandon the classical Newtonian Galilean equivalence principle. And so Einstein said that he built his theory on the backs of very important people, such as Maxwell. He did a number of other things, but he credited some of the giants back then. Now, quantum mechanics also came around at the same time. It's ironic that Einstein got his Nobel Prize for discovery of quantum mechanics. He should have been getting a second Nobel Prize for relativity. That was big enough. That's one of those big enough things that he should have gotten his second one. The committee was saying, well, he's already got one. Let's give it to somebody else. But he deserved two. I mean, Marie Curie got one because she did it in two different fields. But Einstein really deserved a second one there. But in that 1910, 1920s, we had these models put forward, and then they were tested. And the amazing thing about relativity is it was spot on. Same thing with quantum mechanics. As bizarre as that stuff is, it's also been, quantum mechanical theory has been confirmed to an amazing degree. But again, that's based upon earlier stuff. So things progress because people keep asking more questions. We just don't stop with saying, okay, we've got relativity, that's in. That must be the way it is. No, we then keep asking questions. Well, what happens if blah, blah, blah? Like black holes were seen originally as just mathematical curiosities until we actually had reasonable evidence that they might exist. And now we have direct confirmation that they exist. We have even direct observation of the zones around black holes. So this stuff always keeps going on and on because people keep asking questions.
So when you were growing up, and since you're probably older than all of us, what was the theory or hypothesis when you were growing up about the universe? Was it Big Bang yet, or was that?
It was Big Bang, because that was 1920. I'm not that old. My father was even that old. But the thing that was being debated in college was whether the universe was open or closed. Right? We knew the universe was expanding. We observed that. Right? That's another fact. Right? The universe is expanding. We didn't know was that the expansion is going. The rate of universe expanding is faster, is accelerating. That was what was unknown. We didn't have the precision yet to know that because our distance measurements were too uncertain. But back then, the big debate was, is the universe open or closed? By that meaning, the universe expands and goes out, but gravity wants to slow it down, right? Gravity wants to pull stuff back in. If there's enough mass, enough gravitational field, that expansion should be halted, stopped, and then come back in. Just like you throw something up, it goes up, stops, and it reverses and goes back down. So you get a big bang, and come back, and you get a gap. That's the big bang, go backwards, right? It's the big crunch, right? and that the close was a nice satisfactory oscillating thing. The open was like you could take a rocket on the Earth with a certain velocity and achieve escape velocity and leave the Earth. Sorry, flat earthers. It's just the way it works. And And that's kind of the same thing of the open universe. If there was a not enough gravitational field, that expansion was fast enough to achieve escape velocity, and then things would just continue to drift off into oblivion, coast away into nothing. And so the open close was a big debate, and there was lots of stuff back and forth. And it turns out that we were asking the wrong questions. And when we had more data, it was inflating. So here's why you want to get an education. Not to learn facts. You do not get an education to learn facts. You learn education to learn how to think and how to ask questions. So it meant that when I saw the first reports from people like Alex Filipenko and Alan Rees that the universe was accelerating, I went, what? Wow, that's amazing. Okay, how do you know? Oh, wow, that's actually a pretty clever way of measuring. And wow, I didn't expect that. So what does this mean? The universe accelerating? Because that's not intuitive. That was not what we expected, right? And that it was neither open or closed. It's this inflating thing. And of course that again is part of science is about questions. So as soon as they discovered the exciting universe, then we had a whole bunch of no questions, which are being explored, some of which are being answered, some of which have yet to be answered.
So are there still a lot of hold-offs on the old versions of the universe of most scientists?
I think anyone that's any credibility has abandoned the steady state theory, right? That Hoyle was probably the last. In fact, he was probably the last notable cosmologist that was trying to cling on to the steady state universe thing. He's and I think if he'd lived long enough, he would have said, okay, I was wrong. But again, that's a danger. When you think something is true and hold on to it as dogma, then you're engaging in things that are closer to religion, right? Science will sit there and say, oh, wow, thank you. I'm wrong. And now I know something, so I can be less wrong, and I can ask, how was I fooled? And what is the implication of this new information?
So have you ever been admitted you're proven wrong in anything that you've been studying?
I mean, certainly, because for example, with Pluto, I had good arguments to say that planets like Pluto that are very low temperature things are these frozen balls of primordial state when our solar system first formed about 4.6 billion years ago. And the reason why you want to go to Pluto is to look at a kind of pristine bit of the universe that is our solar system back in its frozen state. It was because here next to the sun, there's all kinds of stuff happening and radiation and stuff banging each other and splitting around. So we thought that a planet like Pluto was going to give us a glimpse to the state of what the early solar system was like. Well, it turned out we were wrong. Pluto is active geologically, right? Even though it's 40 degrees above absolute zero, it's actually, and look at it, and it has mountains, it has faults, has tectonic things, it's got flows of stuff, it's got all this, and it's got these weird mountains inside moats and other strange things. It's a pretty dynamic place. It's got an atmosphere with layers. It's a complex world. And now we know, in fact, that most planets. Okay, the other thing is that we thought that planets were rare, right? And this has been one of the great things about the search for life in the universe, is that we thought planets were rare and that we were in a nice spot where we had some planets formed. It turns out that in fact we now know, because we can now have good enough telescopes to measure the surrounding regions, out to maybe 1,000 light years or so, and we know now that 70% of single stars like our sun have planets, and 30% of multiple stars like binary pairs have planets. We know that there are more planets than our stars. So in our galaxy that has around 200 billion stars, there's at least 1 trillion planets.
Yeah.
And the planets come in all kinds of varieties. So that was another example where we were wrong. But I went to school not to learn facts, but to learn how to think and to appreciate what the implications of the data is when we get it. That's part of the thing. That's why you don't go to school to learn the dogma. You go to school to learn how to think. And when you see these amazing things happens, I remember when I saw the inflation thing going forward, like, wow.
Yeah, I remember when I learned that our star, as big as it is pretty puny in the universe.
But I do the other way around. I think our star is pretty magnificent.
Yeah,
and the universe is even bigger, right? I know I'm pretty important to myself, at least I think so. And so I don't feel small and tiny and insignificant. I invert the fraction, right? You're not one nth, tiny nth of stuff. Your value is 1. You are a value of 1 to yourself, and the universe is a even bigger thing. So instead of feeling small, feel like, wow, this is really my favorite universe. It's amazing.
But like I said, but anyways,
but
we got a question in the chat. If you know what that is.
Sure. So we have now. I understand this because Susan has banned me for life from YouTube, so I don't have access to YouTube. Because I made a joke which could have been offensive to Australia.
You can see that. You see on the screen. I put it up on the screen. You can see it.
Let's see. Everyone can see and hear you. Okay. Question: why do people think that black holes lead to another dimension or something? Okay. There is actually theories that suggest that black holes inside black holes lead to new inflation zones. That it says inside a black hole could be another universe, right? There's a style of inflation theory that black holes lead to new universes as part of the multiverse, and that once you cross the event of Brownlee, you're into a different regime. That has not been verified, but there is now some serious talk about black holes being other stuff. In fact, it's kind of funny. There's in fact almost a similar argument in biological evolution to inflation evolution. And our argument goes like this. Again, not yet verified because we need to have more data, but that when you have one of these inflation things where space begins to rapidly inflate, the inflaton field drops down to its vacuum state and inflation stops. You have these bubbles. When you have these things occurring, you set into motion the parameters of that universe. Some of the constants get sort of set into stone. And the thought is that things they just have random values, right? That they're somewhat derived from their perhaps their parent universe. So one thing is that black holes are spawning little baby universes inside their own little universe. From our point of view, we see a contained zone, the event horizon. But from inside, they may be seeing a whole entire universe that's gone through inflation, and their concept may be slightly different than ours. But the notion is that how do we get black holes? Well, we had to have a universe where the speed of causality, c, was a close to reasonable value that you can get atoms form. Because if you get the speed of light to being too slow, then atoms collapse and you don't get, protons, electrons collapse, and the whole thing doesn't work, right? That's one of the reasons why these I hear arguments about, well, maybe the speed of light was different back then, and so the universe isn't so old. Like, no, right? Speed of causality is baked into the universe, pretty solid, and if you change the speed of causality, a whole bunch of things don't work. But we can see physics going back. We can directly see physics going back from now back to almost 13.8 billion years consistently. We see it working. And we see the effect of the speed of light being constant in our universe. It's possible that the speed of light might vary in these other universes, but again, we don't know. So it's a model. Not confirmed, but it's a model.
Speaking of black holes, did you see that movie Interstellar? What's it called? I think it was Interstellar.
Yes.
Is that the one where they went on down that planet for like a 5 minutes or 10 minutes, but up on the spaceship? It's like 8 years had passed.
And that's one of the amazing things. That one of the amazing concepts is special relativity. that Einstein first did in 1905, I think it was, where time that there's no universal clock, right? There's no grand clock that's common everywhere. That every place has a rate of time as well as a motion in 3D space, and so you get, because of one of the consequences of causality being a fixed speed in our universe, one of the consequences is that time slows down. Let me take you through a thought experiment. Again, from Newton's point of view, Newton actually really thought that the speed of light was infinite. Now, if you get infinite speed, then everything everywhere is instantaneously everywhere, and you have no time, and that just doesn't work. But so maybe you say, well, Newton, it was not infinite, it was really fast. Well, it turns out it is fast, but the speed of light appears to be constant. If I have a rocket coming towards you at half the speed of light, and then I send a beam of light, a headlight on front of my rocket towards you, Newton would say, well, the rocket's going half the speed of light, and the light leaves the headlamp at speed of light, so it should arrive at you at 1.5 times the speed of light, right? 1/2 plus 1, 1.5. But it turns out that's not the case. It's always c. So how does it work? Because if you're going half and you do 1, shouldn't it be 1.5? Well, what happens is time slows down. That what you think would be 1.5 turns out to be 1, and part of how it was 1 is that time is running at a different rate. Now, this is not just some theory of things. We have a spacecraft orbiting the sun right now, right? And it goes in very close to the surface of the sun. I mean, much closer than Mercury, but not. And it's measuring conditions next to the sun. And that spacecraft gets going fairly fast. The last time it went in, so it goes basically. Here's the sun. It comes in and speeds up, zips and runs back around. But when it's doing that zipping around very close to the sun, it's going at tremendous speeds. For something it's the fastest large scale man-made object.
Is that so that it can escape the sun's gravity? That why it's so fast?
Well, yeah, I mean, you don't want to go into the sun because then your probe doesn't last, right? We're trying to measure the conditions of the solar wind closer and closer to the sun. Now, it's every time it comes in, it gets a little bit closer, a little bit closer. When it comes back out, we fire the rockets to have it slow down so it'll go in a little bit closer each time. At some point, when it goes in, it's going to go in too close. It won't be able to shed its energy and it'll go poof. But so far it hasn't. And the last time it went by the sun, it reached a speed of 212,000 kilometers an hour. Now, that's not 300,000 kilometers a second, but we're getting to the point where it's getting to be a tiny small fraction of the speed of light. We have on board a clock. And when it's out far and it's far from the sun, we sync our clock. It dives in there, takes its measurements, comes back out, and it says, "Here's the time." That time is different than our time on Earth, because as you speed up, as you go into a stronger gravitational field, you're getting closer to the sun, more gravity, and you're speeding up. Special relativity says your time will slow down. And we see that when it comes back out. It's not just a mathematical trick. The clock actually literally slows down. And when it comes back out, we can measure it and say, what time is it? Oh, you're slow. And we have to tell it what the new time is because we want to agree and so forth. But we can do these exquisite measurements to see.
How far off is the time? Do we know?
I mean, it's measured. I think the errors are in the order of microseconds, right? Because I mean it's going less than like around a tenth of 1% of the speed of light. So the relativistic, I could do the calculation, but the Lorentz transformation for that is not huge, but it's enough we can measure.
So it's not like months off, is this microseconds off?
Yeah, but still that's it still is so if I do 1 minus 0.000001 over 1 squared and squared there, and I'll do that thing. I'm doing like relativity calculations here on my calculator, and we have to do the square root of that. So we have to do the square root of that. Okay, I'll get you the calculation here, and we'll say let's subtract 1 from that and do the reciprocal. And it's 1 part in about let's see, times, so 1 part in 200 million.
Okay.
So if it's running slow about 1 part per 200 million. So if it had a day, if you're talking about a day's worth of time, that is, after a day, it would be slow by about, after 1 day, it'll be slow by about 1/2000th of a second, right? So over 1 day, it would drift 1/2000th of a second.
All right.
We can measure, and by the way, the relativity predicts its speed, and it comes spot on in what general relativity had. So
Okay.
Einstein's right yet again.
So Tony, Ben, you guys have been quiet this whole thing. You guys have any questions or comments or anything?
Yeah, I have some questions, but when Landon gets going, you just gotta let him keep going because it's so interesting. I can't remember all the questions, but the one I do remember is just some kind of conceptual error I probably have. I don't know if I should wait for him to come back.
I'm here.
Okay, it's when the universe at the beginning of the Big Bang or towards the beginning was in such a small area, and it doesn't really matter if it was a singularity to me or 1,000 meters or anything, but at some point you're thinking everything in the universe is in this tiny area. Isn't that dense enough to form a black hole? Why did it not form a very large black hole the size of the universe?
Very, very, very good question. Well, first of all, one of the things, and terms are important. When we talk about, the universe being hot and dense, what we have to say is that our observable universe right now, back right after before inflation started, was small and compact. The universe still may be infinite, right? It's just that our universal universe right now, which it's taken light 13.78 billion years to reach us, but it's inflated, so it's actually about 65 billion light years in radius. Our universe, shortly after the Big Bang, the visible universe we can see was scrunched down to a very compact spot. But the question is, well, why did it not form a black hole? And there's a couple of explanations for it. One is that it didn't have time to do it, right? The second thing is inflation ripped it apart, right? It didn't have the ability to collapse in on itself because inflation was part ripping apart. And by the time it could have collapsed in on itself, it was already expanded. Now, this is another thing that inflation helps on. There's another things about lack of monopoles and other things that are there, but it's one of the things that and understand the universe may be infinite, right? So it's not the case that the universe was small. Our visible universe we can see now was much smaller.
Okay.
So imagine you've got an infinite ruler, and you've got let's say you've got centimeters, and if I take that ruler and I cut the distance in half, I still have an infinite ruler. Mm-hmm. It's just the marks are closer. The grid is smaller. So I like to make sure, as I say, that our visible universe was started as a very small, compact thing, but the universe itself, it might have been, and was infinite. And then why it didn't collapse on itself? It didn't have the time to do so. I mean, one of the reasons why particle accelerators, if they do form black holes, won't swallow up and endanger the Earth, is that also there's a thing called Hawking radiation. Stephen Hawking showed us that black holes aren't so black. Right, that they actually do radiate, And the science is the mathematics is pretty solid. We are looking for ways to confirm presence of Hawking radiation, so we don't have the direct observational thing. And it's kind of bad he died, because had we had that observation, no doubt Hawking would have been observed a Nobel Prize. But you can't get a Nobel Prize if you're dead. So sorry. Even so, one of the things is that our Big Bang model and the universe went through these phases, these transition phases, suggests that there were primordial black holes that did form, but they evaporated very quickly. Why did black holes evaporate? Because I thought, like, it's the beyond here, it's be like can't escape, How could they evaporate? Well, it turns out that quantum mechanics, this is where quantum mechanics and relativity kind of run in each other. And the result seems to be is that, first of all, nothing has a precise measurement, right? The edge at which the gravity becomes so strong that light can't escape is not a hard billiard-balled edge. It's a fuzzy boundary, appears to be. Second thing is that vacuum that has nothing is not no energy. Quantum vacuums actually have energy. There's a quantum field in it, and the stuff is oscillating back and forth. In fact, what you have is basically the field is interacting with itself. It is if you will, it is actually self-interacting, and this self-interaction causes these small vibrations causes virtual particles to pop out of existence and then class back in and stuff. So it's like you have a zero and you get -1 and +1 for a little while, and then they come back in and form zero again. But you get this oscillation, these fluctuations. Well, next to this black hole edge, even though it's fuzzy, you can get a pair of particles that create, and one of the pairs of particles goes into the land in a return, and the other stays out. They can't recombine. And the result is that you get a particle that becomes real. Well, you just can't create something out of nothing. What happens actually is a process that the energy from the black hole leaks. And the rate that it leaks is infinitely proportional to the area of a black hole, not its volume. So giant, very massive black holes that have really big event horizons leak slowly. The ones that are tiny leak very fast. In fact, if there were any small black holes that were created during the universe, the ones that were probably smaller in mass than, let's say, Mount Everest, have long since evaporated. Right, the tiny ones are long since evaporated. The ones that you could form in a particle solar, if you get that kind of energies, would decay so fast you couldn't even get light into it. I mean, it would, by the time you sent light in to see if you could put something in, it's already decayed. Right, so the tinier the black hole, the faster it decays. So in the early universe, the universe didn't collapse on itself because of time, but there were spots where it did form black holes, but those black holes radiated fast and decayed. And so that's why we don't see all those primordial black holes. It was a shame, because it would have been nice to have all these micro black holes around. You could do fun things with them.
I think that's what the Romulan core engine is based off of in Star Trek, is an artificial singularity that's large enough to last a couple years, but I think it's the Hawking radiation they harness the energy from that.
That would be an interesting. I mean, certainly. Now, the Hawking radiation is on black holes that stick around long enough to observe, tends to be lower. It's the micro ones that go out with the bang. So we expect, if we were able to achieve, and there's been, looking at what it might take to create accelerator to create this stuff, you might have matter antimatter that slams together and get this really dense, hot, dense ball of energy that's enough to form a black hole. But then that black hole would begin to undergo Hawking radiation, and by the time you get any other particle given near it that even could approach it, I mean, the speed of light, even a photon, it would already been and decayed. So what we would see is this thing collapse, and then this tiny pause, and then a weird burst of radiation, equivalent to the energy that came in, but it would be oddly delayed, and so we're looking for the signatures of that. We don't think that accelerators like CERN have the energies to do that. There is plans for building a larger Lindner accelerator that might be able to reach that, and that would be a way of generating the black Hawking radiation, which would tell us, again, much more about that era. We're going to go back to the first trillionth of a second after the Big Bang, which is pretty good, but we would need to get back to the first trillionth or quadrillionth or quintillionth of a second to get to those micro black holes. That the universe had a lot enough time after inflation to form, but then they radiated and went poof afterwards.
So, how long after the Big Bang did we have, like, I think that's already out? Did we have, like, what we call atoms and matter and stuff?
Again, I think, if I recall correctly, that atoms were something on the order of minutes, but don't quote me wrong, because that's one of those things I should have studied up on there. I mean, at a later time, I can give you, if we want to do a different show, okay, I can give you sort of the chronology as we understand it, right? And I would basically work backwards of each state and talk about these phase transitions. But I think it's on the order of minutes, but don't quote me on that.
Okay, so,
I'd have to do the calculations and.
Okay, so technically not that long.
If you waited about an hour, I was trying to derive those calculations, because that's one of the standard things. You can derive that, compute that, but I didn't with all my calculations, or I didn't quite get to the stage where I could determine that. But it also is. I can look it up.
Yeah, I don't mind having multiple part things.
I got a question for you. I apologize that it's going to require a little bit of preface here. You were talking about science. The reason you took science was not to learn facts, but to learn how to think. And I agree with you. I felt the same way, but the vast majority of the people we know, or that I know, and that I think most people in this country probably took science because it was required to graduate from high school. And when you tell people like that you want to learn how to think, they think it's a conspiracy where we go to college and we're taught facts on how to think. And it's almost like it's a conspiracy. I've heard the term book smart. And my memory of college is that every science class I took, we didn't just learn in class. We had to take a concurrent lab class where we performed those experiments. But the thing is, those experiments required a whole lot of measurement, a lot of very mundane stuff. And it occurs to me that if you were to teach science from the ground up, from making measurements to then forming hypotheses, you're just not going to be able to interface at the high school level. I may be wrong here, but I was just wondering, what would your thought be on how to teach science to people that probably aren't going to go into science, but yet still vote on policies that affect you?
That, Tony, is an outstanding question, and a lot of people have spent a lot of time thinking about that. You know, you've actually an extremely critical question that the fate of civilization hinges upon, right? And I say that because when you have policymakers making policies based on emotion and based upon religion and based upon mysticism, based upon speculation, you get all kinds of crazy stuff happening. And again, this is not any one particular party or any one particular politician, right? So essentially, when you said something and you talk about people being book smart, well, books contain facts. They don't contain reason. So someone who's book smart has been able to memorize facts, but they may not be able to understand those facts. And that one of the problems that I see in education is that there's a lot of emphasis with some teachers in regurgitating facts.
Is that what they mean by the difference between knowledge and wisdom thing?
It could be, but again, it's a matter of do you memorize the integral tables, or do you figure out how to derive an integral? Do you memorize the processes, or you derive it, right? You prove it. That's again part of this information versus just raw data. So how to think, right? It's a really matter of saying, well, how do you learn? How do you evaluate? How do you go about even the scientific method? How do you challenge stuff? Part of it is you've got to get people to be comfortable with saying, I don't know. So like, for example, when you asked me about the era when the gluon quark plasma turned into nucleons, and I was thinking, but again, I was guessing and saying, I don't know, but I can rederive it, right? That's knowledge. I happen to not have that fact in mind. And it was one of the things I was racing around to do to get all this data there. So I could have gone and said, oh yes, it's blah, 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 right? I can look it up. But again, it's more important for you to understand how to derive things than just to memorize. Mathematics is about this poetry of logic. It is not memorizing the additions table and how to do long division. Okay, there's some things you need to know, right? Because just like in your, if you're going to write in the English language, you need to know how to spell, you know how to print letters, you know how to compose grammar, right, in reasonable ways. So you need to have some knowledge of it, but you don't memorize novels. The way we learn to be an author is not to memorize books and then just regurgitate them. You master the principles of the language. You use the mechanics of spelling and grammar to convey meaning, and then you bring new meaning and new ideas and create new novels. Same thing with science, right? You have to know some of the basic facts, like what's hydrogen, what's helium, some of those things. You need some of that basic foundation on, but you need to know how to build
the ions. I almost failed chemistry because I had a hard time memorizing the ions.
Oh, and organic chemistry is... Besides stinking, right? That's the other thing I didn't like about organic chemistry is it stunk to high heavens. But it was also, but again, it was actually very important. But I was more of a fixing. I was in inorganic chemistry, and I was in a nuclear chemistry, and it's a shame because there's some marvelous things in organic chemistry that I've had paid more attention to it, and got paid more attention to the concepts. But it's hard to be master everything, right? I'm not a biologist. I'm not a physiologist. Not an epidemiologist. Those are areas that I didn't dwell in. I guess I took enough of a course to pass, but I'm not trained in thinking. But still, but they're complementary. And I had, when I was having a conversation with Richard Dawkins, I was remarking that it is remarkable how they can take strands of DNA from two different things and then work backwards of how those evolved and estimate the age of the common ancestor. They can do that for all the tree of life. And in fact, everything they found that they consider life is on the same tree. That's one of the things we're looking for, is something else that's on a different tree that might arrive from outer space. But Kent's thing about the pine tree and the elephant, or whatever his crazy stuff is. Yes, you'll go back far enough and you'll come back to a common organism, and they can look at those DNA sequences and actually tell you how fast and when it occurred. And I found that amazing, right? That's the evolutionary genetics is extraordinary in what they're able to do. And I remember I expressed that. I said, "Wow, I'm not that I'm doubting, but I'm amazed at what you can do just looking at the records." And he says, "Well, but Landon, you take 17 photons coming from some ultra faint galaxy, and you can tell me its age and its temperature and its size and so forth. I find that amazing too, right?" But he understands the principles. I understand his principles. I'm just not versed in I don't have the foundation that he has in genetics, and he doesn't have the foundation in cosmology that I have. But we do appreciate, because again, we ask questions. And so we spent time asking each other questions about how do you do and what happened about this. And I was into DNA encoding and so forth, and he was asking about how photons and what if there was dust in there that reddened things, and we had a good time admiring each other's expertise. But still,
Yeah.
I wish that science was taught in a better way. Mathematics was taught in a better way. Yeah, you still have to have some facts. Just like you need, it helps to be able to do rough calculations in your head. So you need to be able to do some calculations. But on the other hand, why in the world would I take a long division of a 3-digit number divided by a 2-digit number, or something? Why would I do that painful process when I can have a computer do it? I understand the processes of doing it. By the way, beware that the stuff you think is trivial can actually be complex, because one of the things I'm working on right now is teaching computers how to divide extremely fast, extremely large numbers, extremely fast. And it turns out that division is a very complex process, and the way we do it with pencil and paper is probably one of the worst ways to do it.
We talked about the theory of Big Bang stuff. What are the scientific laws that make up the theory? Or is there any?
I mean, certainly gravity. Certainly, laws about things like E equals mc squared is a fundamental thing, or that's with the rest mass. The E squared equals m squared c to the fourth plus. There's a momentum thing. There's a E equals mc squared is the Einsteinian mass energy equivalence when things aren't moving, in your reference frame. But there's another term you can add when you get to motion stuff. But that's one of the fundamental things. Another thing, I guess, laws in so gravity, electricity and magnetism. Some of the Maxwell's equations are laws that are fundamental into that. Geometry, some of the things like Lorentz contraction stuff, and mathematics is considered as relative laws. So there are some basics of things that if you don't understand, it's harder to see the implications of it. You can still appreciate the strange stuff. Relativity gets into really odd things. Not as odd as I think quantum mechanics is even odder than relativity. And I'll say that early on in my childhood, I was born and raised a fundamentalist Baptist, and my fundamentalism was running into problems with science, and in fact, particularly quantum mechanics and some of its strange applications kind of ran against my fundamentalist beliefs. I did spend some time railing against quantum mechanics and trying to prove it wrong. But see, there's back to the science. I didn't sit there and say, "Oh, quantum mechanics is unbiblical and therefore it's wrong." Right? I said that doesn't seem plausible. Let me prove that quantum mechanics is wrong by designing experiments and catching it. And had I done that, by the way, I would have been a really, really famous person. But instead, quantum mechanics won. But as I say, that challenging, that again is part of, even when I was a fundamentalist, I was still asking questions. But I have to embarrass and say that I actually told none other than Richard Feynman, when he was describing quantum electrodynamics to me, I actually said, "Well, now you're just being silly." He's describing the bizarre things of that. But he was patient enough to keep explaining, keep going on, and he encouraged me to go off and say, "Okay, if you think this, if you have a way of disproving it, please do so." He encouraged me to try to disprove it, and how to set up experiments. And I spent a lot of time, a lot of experiments in college that weren't assigned. One of them was measuring the speed of light. Another one was trying to catch quantum mechanics in the act.
Oh.
And speed of light was pretty good. I was pretty solid about that. And the quantum mechanics beat me. So
you were one of the people that were like, you tell you wrong. You're like, "I'm not listening. La 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 la, not listening."
No, but I mean, it was part of the problem was that it was Feynman that taught me the principles of first general relativity and then special relativity. And again, you go through the math and the way, Feynman's, one of his masterpieces was to take very complex subjects and present it in very simple but precise terms, right? So he doesn't dumb it down to the point where it's wrong, but he's able to explain it without a lot of the language, what we call the language of the priesthood, right? And so he took me through relativity, and I have to say, the way that Feynman explained relativity is like pretty obvious, right? And it's not now the consequences of it are unusual, like the twin paradox and time slowing down and so forth. But once you see the principles, then those consequences are amazing. They're not that it's wrong, but they're amazing. But then we went to quantum mechanics, and I was coming to quantum mechanics from a relativity point of view. I probably went through some of the same things that Einstein did, where he said, "Come on, right?" And how could this be? But I had the benefit of a lot more knowledge than we understand a lot more today than he did back then. And I also went through a lot of experiments and tried to disprove quantum mechanics and failed. But that's fine. That's about asking questions, right? It would be. I wish religious people would do that and say, "Do you really mean that Abraham was going to go and kill his son and commit a murder in the name of the Lord? I mean, is that really right?" But you can't do that in religion. You can't ask questions. You're given truth, right?
Did you perform your own double slit experiment?
Yeah, and also tried this triple slit experiment. And in fact, one of the things I did was I created a source where I was using electrons, beta particles, going through the slit, and I took copper sulfate crystals and embedded into them radium, which would had a decay mode where you could kick off at a beta particle, right? It was an alpha emitter, but the radioactive substance, one of the decay products, was a beta particle that came out. And so I used the beta particles from the decay, and when the beta particle zips through the crystal, it breaks bonds, right? It zips of energy. So I had two narrow slits. I had an emitter, and the electrons would go out, and then on the back screen here was a spot when they hit, you could actually get a spark, right? So I could see that I see a flash. I knew the beta particle hit there. I'd record where it was. I'd pull the crystal out. I'd look in the crystal under a microscope. I would see the trail. The way you can chemically treat it and see the destruction of the crystal lattice as that electron's going zipping through, breaking bonds on its way out towards the slit. So I knew a particle left from that spot, went through one of the slits, I thought, and ended up on the side. So if I have two slits like this, and the source is back here, you'd think the two shadows would be these two columns.
Mm-hmm.
But they're not. There's this interference pattern. One electron at a time was going through the slits, one at a time, and it was interfering with itself. It wasn't a BBs and two slits, and therefore the open spot was where they hit. No, it was a wave function. It was interfering with itself, going through both slits, and stuff. It was.
Yeah, quantum mechanics makes me think the universe is fake because it's so counterintuitive. It makes no sense.
Yeah, in fact, that's one of the arguments against intelligent design. No intelligent person would design the universe with quantum mechanics. That's a bug. It seems to be a bug, right?
It's interesting that you guys say that because I married a quantitative psychologist whose entire job is psychology, but with statistics. She studies the psychology of masses, and just hanging out with her over the past 20 years about. One of the things I learned is that just about everything in reality is statistical, and it seems like quantum mechanics is statistical reality. Whether it seems to make sense to you on the surface, when we make a prediction on where an atom's going to end up or where an electron's going to end up, it's almost always what the statistical probability is. It's never very exact.
And statistics is a way that the statistical fields is a way that we try to mathematically describe it. The thing that is also there, because certainly statistics is an important part of how you can do quantum mechanical calculations. because one of the problems is that people think there's an answer to every question. And give you an example of quantum mechanics where it says, no. You have a particle going through or a baseball going past. You cannot know precisely its position and its momentum at the same time. In fact, asking the question, where is that electron and how and what is its current, what is its speed precisely is not a valid question because there's not an answer to it. The notion that things are in one spot and they go this way and you can measure it and so forth is quantum mechanics says no, right? That it's not you're not clever enough. It's not that you're not careful enough. It's not that you're not precise enough. There isn't an answer to that absolute question of where something is and what is its energy state, or where something is going, what its position and momentum, or various other parameters. And the notion that everything has an absolute answer was something very attractive to Newton's time, right? Newtonian mechanics seemed to be pretty good for everyday life. And the notion that if you just knew the state of the universe, the state of the clock, you could just use physics laws and just predict absolutely what was going to happen in the future, what happens in the past with perfect precision. And the answer is no, you can't do that. And weird things like chaos theory, things like quantum mechanics show there's limitations to questions. But even you say, okay, so you're not good enough in your lab. Well, even mathematics has limitations. Something as you think is concrete as math. Any system of axioms and logic that are complex enough to just derive the number line, number theory and how numbers work, any system you do that can do that is either inconsistent, meaning that it has contradictions, or it's incomplete. There are things that it can't, there are statements it can't resolve. So any system of axioms and logic will produce either something trivial, like you have a logic system saying everything is itself. X equals X, and that's it, right? Okay, trivial, right? Or it's incomplete, that there are statements you can't prove, or if you get, or it actually has violations and contradicts itself. Incomplete, inconsistent, and trivial. So there are limitations to logic. There's limitations to measurement. There's limitations to stuff. Even something. Here's one of the things that's amazing about dark energy. If dark energy continues to behave as we see it doing, and it continues to behave that way in the future, it means that if you were able to live forever, there's only a finite amount of stuff you can do. If you somehow had eternal life and even amount of time, there's only a finite amount of things you can do, finite amount of calculations you can do. There's a limitation, fundamental limitation to even eternity, based upon things like the decay of so-called stable particles and inflation, a big rip, and so forth. It appears that there's limitations to omnipotence. That has kind of profound effects on deities and so forth, but there it is, right? It is amazing in that sense.
Yeah, this makes me a little funny, real fast. Like, if heaven exists, like it's the scientists up in heaven discussing things for thousands of years, doing experiments up there.
Yeah, but it's a thing that eternal life isn't all what it cracks up to be. It's actually finite, limited in what it can actually do, and that's kind of an interesting implication in and of itself. Now, from the point of view of these other the multiverse, that might be different, but at least in our universe, it appears to be limited. But again, those are questions being asked. But
yes, because that I heard something like a theory about that, or I have about that, where there's different universes inside the entire cosmos or something.
Well, there's possibility that the multiverse is a eternal inflaton field where you get these fluctuations, and occasionally you'll get a fluctuation that'll occur where it'll bump up, it'll stay elevated as local space will rapidly inflate, and then it will drop down to a lower energy level, and the result of dropping down is that the particles become real, and you now have a universe bubble that is formed, its own time, its own spatial, popping out of this existence of the multiverse. But it's said that in our universe, one of the things that is this limit on omnipotence is that there is a maximum calculation the universe can make. There's actually implications in cartography. And the argument goes like this: take our entire visible universe and turn it into your own quantum computer. Let's say quantum computers actually work, and they work marvelously well, and you can program them to take the entire visible universe and make it your own quantum computer. Of course, you want to shrink it down because you don't want to have 13.8 billion years of time for just a signal to go one way. That's not a very fast computer, right? So you want to shrink it down. But don't shrink it down too much, because if it goes into a black hole, then you can't get data in and out. It's not very useful. So you want to shrink it down. You want to grab hold of the universe as visible universe that we can interact with, and bring it down to a stage not quite to a black hole, but dense, so that signals flow back and forth, and make its own quantum computer. Now, of course, part of the problem is that you'll get decay of particles. You get inflation. Dark energy messing you up and putting limitations, but there's a limit on what you can do. And ask, what could that computer do, right? And it turns out that there is a limit on the number of calculations that computer could do, and it's a pretty big limit on there. I mean, the universe is capable of running somewhere around 10 to the 2 to the 525 power, right? Which 525, and if you look at the digits of that, it's about 10 to the 159th power calculations that the universe is capable of doing, right? Even if you have as much time as you want. But by the time eventually the universe turns into just a useless sea of photons, or all your black holes that decay by Hawking radiation, you just have this cold universe of photons with no temperature difference. You can do any state transitions. And so if your algorithm requires 1 with 160 zeros after it, it's very likely this universe can't do it, even if you have an infinite amount of time. It's one of the implications of dark energy. Now, there's a lot of stuff we don't know about dark energy, but one of the implications is that there's a limitation on what our universe can do. Could the multiverse do something? Yes, but it's hard. We don't know how to communicate between those other universes. Those universes that get born out of the inflation field may be so far apart that they can't communicate each other, and so their answer, we don't know, right? So, but there's interesting implications from limitations of omnipotence on that. But again, yes, I think, Tony, your question about how to try and get people to learn how to think. Learning how to think is actually considered dangerous, right? Particularly religious systems did not like people who thought for themselves. Galileo's crime that he still is guilty of, right? The Vatican have pardoned him asked for pardon for Ray Rodriguez in his trial, but they did not pardon him. Galileo's sin, he asked questions. Galileo was not qualified to challenge the authority of the church and ask questions to try to verify what the church was saying. And he remains guilty of asking questions. And in fact, I had because we were at the Vatican Observatory and had this bishop to try to do this. Well, but we've forgiven Galileo. And I said, well, first of all, by the way, I went in 2004. I went to the prison you guys put him in to do measurements of the transit of Venus to help measure the distance of Earth to the Sun in a much greater precision. But secondly, if you believe in sin and confession, you should go to confession because you have just told a lie, or you've lied by omission, or you're speaking untruth because he has not been pardoned. He was guilty of asking questions. He was guilty of being a scientist. And that's came for what you did to Giordano Bruno, right? You burnt that guy at the stake, who was suggesting that stars were other planets, stars were other worlds, other suns that might have other planets and have other civilizations and he even said other even Jesuses might have been there and so forth. And you burnt that guy at the stake, who was one of the first to postulate that stars were like our sun. Our sun was like a star. But as I say, the Vatican does not reign. I don't let them get away with much. They're guilty of a number of things, amongst which is not liking people asking questions.
So he was that because he said the Earth was the center of the universe. That was the crime.
Well, one of the things was that Galileo got it. I mean, where he ran into political trouble was that the Medici brothers wanted to be declared by the Vatican to be their own kingdom, not just a ruler, but they wanted to actually have the church appoint them as saying, Bonk, you're one of these holy rulers appointed by God to rule. Here's your kingdom, blah, blah, blah. And so they were bargaining with it. And they had, Galileo was causing the Vatican problems. He started off in Padua, where they were fairly radical at the time. They could tolerate people challenging the church. But when he moved to places like Siena and Florence, that's where he ran. He moved into the zone where he was actually traded. They traded turning over Galileo with for political things. Now, one of the things that Galileo did that ran into trouble was not just the publishing of the stuff. Galileo was a teacher, right? And one of the things he was doing that the Da Vinci rulers had him do was to teach their children and the children of their important clerks and scribes and so forth. He was kind of the lecturer, if you will, and trying, because they valued his knowledge, right? Galileo's use of the telescope that he perfected, he didn't invent, but he perfected the telescope, was used very much in commerce, where in like Siena, they would use telescopes to look far away to see a ship coming over the horizon, the curved horizon, flat earthers. They would see the ship come in, they would see the flags, and they would say, that is the flag of such and such a ship, and they're coming from Egypt bringing wool. So let's go and drop the price of wool. They want to buy flax. So let's temporarily increase the price of flax and drop the price of wool. They come into port. They say, hey, let's trade, blah, blah, blah. And they were actually becoming quite wealthy because they were ripping people off by seeing the ships coming well before they got into the harbor and changing the prices, right? He even did that to the Vatican had ships trading around because the church was making money, and he wouldn't care whose ship it was. He wanted to make his rulers money. They in turn employed him to teach and to do fun science experiments. So that was kind of his shtick, and he was kind of a thorn in the side. Oh. But there was a famous dinner, and in the dinner he was doing his usual talking of stuff, and he held up a grapefruit, and he held up a small like tangerine, and he was teaching the kids, and he said, if I drop these same time, which is going to hit the table first? And big big tangerine, small little, I mean, big grapefruit, small tangerine. And the kid said, well, the heavier one's going to hit first. And then he turned to the bishop and said, what does the church say? And the bishop, quoting the Aristotelian logic, said, well, the grapefruit being heavier has greater need to reach the ground and will hit the ground first. And then Galileo dropped the two and they went. Now, he wasn't being asked to say, hey, you're wrong, but he then turned to his students and said, well, explain what you just observed. Why did they both hit the ground, hit the table at the same time? The bishop was upset not because he was proven wrong, but because Galileo questioned whether he was right. So that was part of the Inquisition. Part of the thing was repeatedly questioning. He did not have the authority to ask questions of the Catholic Church. And if there was a hell, I wish that a number of them would be confined to that, for those thought crimes. And he still is. They won't. I don't think the Catholic Church would be too happy for people asking questions that are considered where the Pope speaks ex cathedra and says, "This is it." Right? I, with authority of Peter, bind in chains this truth. Blah blah blah. Speak ex cathedra. This is truth. They don't allow that to happen.
So then,
you don't allow that stuff to be questioned.
Sorry. So no one ever before. Probably before Galileo, did no one ever think about putting that telescope up in the sky instead of looking for ships?
Well, I mean, certainly Galileo was one of the early people that used telescopes to look in the heavens. Other people did too, by the way, because he didn't invent it. There were two people that discovered the moons of Jupiter and published it around the same time, and they were like within a couple of days. And Galileo saw two of the Galilean moons, and this guy named Matthias saw two of the others, and they say had an argument over who saw them first. But Galileo helped perfect using of telescopes that came in from, I think it was invented in Holland, and he was one of the early people to do measurements and look at stuff in heavens. And in fact, he even observed Neptune, right? He would draw star charts, and one of the dots he had was with Neptune. But the problem is, Neptune, the Galileo's telescopes were awful. I looked through his third telescope, and it really is kind of it was great for its day, but today's thing, it's not all distorted and so forth. It's not very good. But if that's all you had, it's pretty good. I mean, he was awful enough that he couldn't see Saturn having rings. He thought it had little lobes on the side. It wasn't until people had perfected optics that they saw the rings. But still, Galileo did a lot of things. He was kind of an interesting showman. He kind of put on these little experiments. He'd like to troll people. He had a big thing where he grabbed a big crowd and he said, he had people take a rock and throw it in the river, right, and say, why does the rock sink? People say, well, it's heavy, right? It sinks in the water. Well, on a cart, he had piled in straw that had gone up to the mountains in the Alps and brought down a chunk of ice. And on a cart, he had a chunk of ice that was covered in straw that they that the sort of slightly insulated, unwrapped the straw, and two strong people took this giant chunk of ice and then threw that into the river, and it floated. And then Galileo went to his students and said, okay, explain. How come the ice floats, the rock sinks, but they're both heavy? Right? And so people would show up to his gigs because he would do these crazy things, and people would be amazed at stuff. It's just that when he embarrassed the church and asked questions of the church, and the church turned out to be wrong, he was charged not because he did not have the authority, according to the church, to question the church. What do you say? But again, that's science, right? It's an interesting guy. There. But again, this is part of the thing about dogma gives you answers. Religion tries to tell you answers. Science tries to ask questions. And if you get some result, it becomes a temporary spot to ask more questions. Never ending. So we have an amazing universe, and you can keep asking questions. But you've got to teach kids that knowledge of stuff. Yeah, go ahead.
Questions bring up more questions.
Yes.
If I can make a respectful, very respectful critique of your answer, is that it wasn't really an answer. You've pointed out the questions, and that they're there. And here's the problem: I don't have an answer either. So when I ask you this question, I'm very sincere because it's really important. It needs to happen. We need to answer this question. What is the best way to teach science from the ground up? How do we get our people that maybe just graduate from high school to understand what science is and be able to respect what it is? Because I mean, in the end, you're right. You both know that in the end, science is what gets us things. If you drive a car, it's because a geologist predicted ahead of time where they would find oil. If you use electricity, it's because a geologist predicted ahead of time where they would find coal. I can go down a whole bunch of lists of the practical applications of science, but I don't know how to teach it, and I would love to do that because if we could figure that out, we could probably solve a whole bunch of problems.
I mean, the short answer is I don't know, and what I said was a long critique on the fact that we're doing it is having problems, and things like flat earther movement, anti-vaxxer movement, and some of this young Earth denialist stuff. Are examples or symptoms that our education system is not as good as it should be. I think that teaching is a very honorable profession, right? When I meet a teacher, I always invariably say, "Well, congratulations," right? That they're very honorable people that sacrifice a lot, but are not highly valued, and they should be highly valued. And so. I guess I say that, and I'm not an educator. I'm not in theory, but I think giving people ability to ask questions and teaching them how to think is a thing, because that's a rare problem. When I look for an intern, I don't look for an intern who knows all this stuff. I look for an intern who's able to think. And if I find that, then all the rest can come in, because then I just give them some information, let them think. That's kind of the key in there. But how do you teach people to think? I don't know.
It's in facts and stuff. I was talking this when I was my head.
I honestly meant no disrespect by that.
No, not say. And your question is extremely important, and in fact, I think the fate of our civilization depends upon it. Your question. So that's why I would honor that excellent question. But I'm not a teacher. I try to teach, but I don't know. Maybe there's better. Maybe you should have someone who's a professional educator on, ask them that question.
Yeah, speaking of facts, I was talking last year when I had Bill Ludlow on my show. He was talking about how sometimes the scientific knowledge, the scientist thing takes a while to reach down to the student level, or the kids, where the public can learn it and stuff. Like, especially maybe more now, faster with the internet now, but like for example, the stuff they learned in the 70s, about like whatever, that when I was growing up in the school in the 90s, I still didn't know that they were in the science books yet, and even 20 years later, it was until I got the internet computer that I even knew some of this stuff that the scientists had known like for 30 years before that.
But in this internet where you have all these facts you can draw upon, I don't know that people are using that well. They seem to be more. There's other things that seem to be a higher priority in using the internet than in learning stuff. But I had one of my I was an intern for a physicist named Teller, and one of the things he told me was that he said that an expert is a person who knows where to look things up. The other thing he said was a person who knows how always has a job working for the person who knows why. So be the person who knows why and know where those things look things up. Don't memorize the integral table. Know that there's an integral table there, or though there's a program that will integrate for you. You need to know the fundamental facts, but knowing why something is the way it is much more important than knowing how something works. So knowing why a photovoltaic cell produces electricity is more important than knowing how you make a solar cell. Right? Because if you want to make better solar cells or improve things, knowing the why, what's happening there, is more important than the memorizing of the formula stuff. And I think we do our children this favor by forcing them into memorization. I don't think we do a favor by having people who teach subjects that don't know the subject.
Oh yeah.
But those are complaints. And they're not answers, Tony, to your questions. They're just laments, maybe.
I'm not. I can't criticize you for not having an answer because I don't have one either.
Yeah. So Bent, I know that Bent, you're no relation.
No relation.
Because it's important, that disclaimer, right?
Right.
Is I know that, for example, in your thing with your the thing with Dapper Dinosaur. By the way, nice. I really like Dapper Dinosaur. When you have these conversations with the likes of the Kents and Kins and so forth out of that, I don't think there's value in trying to convince those people. Their intellectual suicide is probably pretty complete. I think there's value in other people listening to the debate.
Well,
what you're doing.
We do Kent with Bent. Well, there's a couple of reasons. One reason is because I grew up watching him on TV, amongst other things on TV, and I fully believed what he was saying. I grew up in a Christian, conservative, non-denominational household, young earth creationism. My dad was the pastor of our church. So, I heard all these Kent Hovind arguments, and I never heard the other side. I heard teachers from my high school give seminars at my church on why evolution is wrong, but I never heard the evolutionist side. So learning a lot, I've learned so much from just watching Kent Hovind and watching the rebuttals, watching his debates, paying attention to what his opponents are saying, And there's another point I was going to make. I can't remember. I think for me, once I realized, and I've gotten to the point where I'm now, where I know Ken's wrong and I know why he's wrong, now I'm trying to understand, wait, it only took me a couple of months of watching these counterpoints to what he was saying. Why does he keep making the same points that have been proven wrong over and over and over again? So now I'm watching it to try and understand, why is he so stuck in that line of thinking? Is it because that's his only source of fame and income at this point? I mean, that's possibly, but I'm more interested in the psychology behind how someone could have these ideas and they seem okay until you learn more about them, but then you just keep sticking with those same ideas. Like Landon, you were saying, you were raised as a Baptist and you started questioning things. Even if you're not questioning, but you're just open to hearing other sides of the story, you're gonna eventually, if you pay enough attention to Kent Hovind and these debates, you're gonna figure out something's not quite right there. And so for me, that's what Kent with Bent is about. It's trying to understand why he's doing what he's doing, why people are buying into it. And I think part of it is people just feel really threatened. Like, if Kent's wrong, my whole religion's wrong. And they've got that belief bias in their head, like their whole worldview is wrong. That's very scary.
Yeah, you raise some.
Going back to what I said before, you got sometimes you got to admit that you can be wrong about something.
Yeah. Well, it's hard to be wrong about your most, your deepest, most fundamental beliefs. It's hard to admit you're wrong about that, because if you're wrong about that, you may as well be wrong about gravity or time or, can you really trust anything anymore? So
I would suggest. I mean, here's a couple of possibilities, right? I will suggest some things that may be going on in the minds of people like that. You're right. That it certainly could be that that's his stick, that's his public persona, and it's an act. But I think I suspect it's more than that. Some people are not interested in having a debate. They know they have determined their right. Truth has been declared to them, or they've declared truth, and they're not interested in your proof because they will say they know you are wrong. And so it doesn't matter what you can say. They start with this presupposition that this is truth and this is right. Other people hang on to that for a couple of reasons. One, because if they've been told this complex, uncertain universe is now certain and here it is, that's a very attractive drug. Another thing, of course, is that the systems that evolve around the fellowship, right? That the society that are like-minded in that spot is incumbent upon you remaining in that state of this declaring this as truth, right? I'm not saying not even you don't have to be in cult-like stuff, but if your family and all your friends and all your social circles are in the same set, to break out of it is a very difficult thing for someone to do. So there's a combination of the social pressures, and that's their entire world. Combination of here are the answers. Why would I want to go and ask questions? And then of course the people that it's their shtick, right? It probably some combination of that. But I think that when you present really logical stuff to the likes of Ken, their minds are going through, they're praying for you, and they declare that whatever you said is false because it doesn't meet with their truth. They before you even start, you are declared wrong. And the only thing they can hope for is your salvation of your soul, right? Now, your work you do is important because, as you said, it's the other people hearing the debate that you can influence. I think that Ken Hovind is and Ken Ham and the people like that have already committed suicide, and they are probably going to go to their grave in that state of intellectual suicide. The thing you might be able to do is to prevent someone else from sinking into that same pit. And that's why it may be that's important that you have those kind of discussions. Hats off to you, because our discussions don't go very far, right? It's a matter of saying, you're wrong, your brain's dead, and I'm not going to debate facts. And they say, you're in a state of sin and you're going to hell. And if you only see the truth, here's the Bible, or the whatever your religious text is.
Right.
But that's, I think, again, it's just like when it was in politics, you're debating opposition. You don't debate opposition to convince them. They're going to go against your bill anyway. You debate in order to have the public and the people that are on the fence see your side and maybe sway the argument. You don't debate to convince the opposition. You debate to inform the audience. And so I think that's where you should, and don't, but people like him, or even people like G-Man or Psy, will try to work at you psychologically. They're very good masters at the psychological and trying to get under your skin and try to get you rattled and try to get you off your game. But approaching it in cold logic and not trying to convince them, but instead inform the audience watching the dumpster fire is perhaps of value. Maybe that's, I don't know if that's the answer, but that would be my suggestion of why I think what you're doing has perhaps some value. And good luck to you, because it is a hard thing. But as I say, I think this is part of this education thing that's there, and and giving people some sense, in science, giving people the wonders of the universe, right? Describing marvelous black holes and planet Jupiter and all this good stuff is a good place to get people to wonder and being able to ask their own questions. So I try not to give them heavy. Jupiter is this many kilometers in diameter and this temperature, this blah blah, and composed of this percentage of blah blah blah. That give them more of the wonder and have them try to then say, well, what about some more? What else could I find out? Get them into that question thing. And if they begin to ask questions and they get a habit of asking questions, then dogma has a really hard time resting and sticking in them.
Yeah, well, as much as I whoever start wrapping this up soon, I'd love to have you on again, like so we could continue this conversation, or like go into more details about stuff.
Yeah, I mean, we could do the history of the universe as we understand it, go through, and that's where I could have the tables. Those are those facts I can dribble down, but do it in context of wonder about how the amazing universe, had the amazing universe evolved. Sorry.
Yeah.
But it evolved. It went from this state to this state to this state to this state, and these transitions, and what we know for very certain, what we know plausibly, and then what we don't know that we're working on. That's the wonder of cosmology, and I just hope I can live long enough to find more questions.
Yeah. Hopefully, but by the time you'll have more. Next time we appear, whenever that might be, we'll have more time to get your research in order beforehand.
Yeah, but there's a few fact tables so far that was going to drone up there, but again, I want to leave people this thing of saying, please continue to ask questions. You live in an amazing universe. It's certainly my favorite, and it some very simple physical principles gives rise to wondrous things. You don't have to resort to genies, fairies, and other extraordinary stuff. The reality is amazing enough without having to add in a bunch of stuff. If you're going to go fiction, read some science fiction, read some classic fiction, right? You don't need to make it part of reality. You can make it part of your experience.
So, Tony, anything you want to plug?
I actually don't have anything I got to plug right now. It's going to be a little while before I put up another video, but just in case you guys want to hear any a fully referenced argument against your favorite creationist argument, by all means check out my channel, Tony Reed, where I have a show called How Creationism Taught Me Real Science. I cite my sources in the description. You're free to read every single one of them. I do my best to make sure that they're not behind a paywall. They often are, but I do my best. There's ways to get around that, but I can't talk about that. At any rate, if you want to see a well-researched show, I think I do a lot of good research. I think that's what I'm appreciated for. I hope I am. But anyway, that's all I got to plug, if anything.
And Tony, you focus on the age of the Earth and geology. Is that what I was getting?
What I do is every week I take on, or for a while every week, I've kind of slacked off in the last month, not last year or so, but I take on a different creationist argument, and I go to the sources. If it's about ocean salinity, or if it's about mitochondrial DNA, I'm going to go to the actual sources first. I promote them, I put them on the channel, and then I report what's there. But I also put the references there because I want people to fact check me. And what's really cool is that the people that watch my show do fact check me, and sometimes I get things wrong. And so every 20th episode, I congratulate them for pointing out stuff I got wrong.
Excellent.
And then I point the resources for them to get the actual information. So, yeah.
Thanking somebody that points out you're wrong is a good thing, because they've done you a favor. So that's
yes,
that's
they have.
And I say one of the plugs I would plug is the Milwaukee Atheists. They're a group of folks that are they do actually a lot of research into religion, and they also have a Sunday show where they actually are reading the Bible, and they read it. And I must say, yeah, as a Christian, I read the Bible, but I read it within the veil of this is what it is. And you just read the Bible. It's got some pretty crazy stuff in it. But again, check out Moakoi Atheists. They do good stuff.
That's the funny thing is, people actually now can read the Bible. Back in the medieval times, the priests and stuff read it to you in Latin, so that
Sure. Sure.
So Ben, you have anything to plug?
Just Kent with Bent. That's on the Dapper Dino channel.
Fun show.
And then I do. I just kind of join in with it. I have a YouTube channel. I don't really use it much. It's not really related to any of this stuff. But I guess if you want, you can check out my YouTube channel. I would say check out the band, coppermagma.com. And free music. We give it away, record it, give it away. We actually have a song called Black Hole that's been recorded. And there's a song written, not yet recorded, called Heat Death, referring to the heat death of the universe. So
excellent.
Some of the theme, it's still music though. But we try to touch on the astronomy themes and stuff like that. It's pretty cool.
Yeah, Dapper, and you're supposed to check out Dapper Dino. He's got some fun stuff.
Yeah. As for me, the only thing coming up on my channel tomorrow is I continue the game of trying to escape from a killer teddy bear.
I believe in you. You can do it.
Well, thank you very much. I hope, and again, I apologize for the things I got wrong. I try to be as factual as I can, and I try to do. But there's a lot of material that I try to brush up on as well, because it's an evolving thing. Keep nettling this up, but evolution is a really good thing, right? You're not stuck.
Well, as I say, never stop learning and enjoy the randomness. We'll see you all next time. Bye.
Bye.
Bye.